Welcome to This Explainer. Today we're doing something a little bit different. We are going to completely demystify statistical hypothesis testing by putting you right in the jury box of a trial. If you've ever found yourself wondering how scientists, businesses, or researchers mathematically actually prove a claim, well, you are in the perfect place. We're going to break down the conceptual logic of testing, look at the opposing hypotheses at play, and actually walk through the exact step-by-step procedures used to evaluate the evidence. Here is our docket for today. We'll start with the courtroom of statistics, then meet our null and alternative hypotheses. After that, we'll cover the burden of proof, dive into Z, T, and proportion tests, and wrap it all up with the formal 6-step procedure. Let's jump right in.
All right, Section 1, the courtroom of statistics and assuming innocence.
Okay, let's dive straight into this analogy because honestly, it's absolutely the best way to grasp what hypothesis testing actually is. At its core, statistical testing is just a formal method to determine if sample evidence supports or completely contradicts a claim about a population. But the underlying logic, it operates on a framework that is surprisingly identical to criminal law. Think about a courtroom. A defendant is assumed innocent until proven guilty, right? The burden of proof rests entirely on the prosecution. Well, in statistics, we do the exact same thing. We kick things off by assuming an initial claim, which we call the null hypothesis, is completely, entirely true. We assume the status quo is innocent, so to speak. From there, we actively hunt for sample evidence against it, and if that evidence is strong enough, we reject that initial assumption in favor of what we call an alternative hypothesis.
Moving on to Section 2, let's formally introduce our opposing players, the null and alternative hypotheses. First up is our defendant, the null hypothesis, written out mathematically as H0. This represents the status quo. It's the baseline assumption that there's no change, no difference, or no effect whatsoever. To put that into perspective, imagine a company claiming their customers spend an average of $500 a month. Our null hypothesis, our H0, is that the population mean, represented by the Greek letter mu, equals exactly 500. We just accept this as our starting reality until the hard data forces us to believe otherwise. Now, sitting on the other side of the courtroom, acting as our prosecution, is the alternative hypothesis, or H1. This represents the actual change, the difference, or the new effect that we are trying to prove. So, if we're testing a brand new teaching method where the baseline score is 70, our null is that mu equals 70. But if we want to prove this new method is actually better, our alternative hypothesis is that mu is strictly greater than 70. We call this a right-tailed test. Conversely, if we're studying a new medicine designed to drop a certain health metric below a baseline of 50, our alternative is that mu is less than 50. That's a left-tail test. Or, if we just want to see if a factory machine is miscalibrated, meaning it's just different from the standard, maybe higher, maybe lower, we'd run a two-tailed test where mu simply does not equal our target number.
Which brings us to Section 3, the burden of proof, and the types of errors we can make.
Now here is where things get incredibly real. We have to look at the consequences of getting our statistical verdict wrong. Because let's face it, juries make mistakes, and statisticians absolutely do too. Broadly speaking, we can make two critical errors. The first is a type 1 error. This is a false positive. It happens when we reject a null hypothesis that is actually, in reality, true. Think of this like convicting a totally innocent person or telling the world a useless medicine actually works. The second is a type 2 error, a false negative. This is when we fail to reject a false null hypothesis. It's like letting a guilty person walk free, or concluding a highly effective medicine doesn't work when it actually does. The absolute crucial point here is that we have to control these risks, particularly that type 1 error, the false positive. To do this, we set what's called a significance level, or alpha. Now, the most common alpha level you'll see is 0.05. This represents the maximum acceptable probability of making a type 1 error, giving us a really rigorous 95% confidence threshold in our results. Of course, depending on the stakes, researchers might loosen that to an alpha of 0.10 for 90% confidence, or tighten it to a very strict 0.01 for 99% confidence. So once we've set our alpha, how do we evaluate the evidence? We use the p-value. The p-value is literally the probability of observing results at least as extreme as our specific sample result, assuming the null hypothesis is true. Just think of the p-value as the raw weight of the evidence against the defendant. If our p-value drops at or below our alpha threshold, let's say we get a p-value of 0.03 against an alpha of 0.05, boom, the evidence is strong enough. The chance that we're just looking at a random fluke is just too low. In that case, our decision rule is crystal clear.
we reject the null hypothesis. But if that p-value is greater than our alpha, we fail to reject it.
All right, section 4. This is the math part. Z, T, and proportion tests. Let's test the evidence.
First up on the docket is the z-test. We use this specific test when we actually know the standard deviation of the entire population, which we represent with the Greek letter sigma. We basically take our sample mean, subtract the population mean, and divide that by the standard error. Now, the standard error is just a measure of how much we'd expect sample means to naturally bounce around based on our sample size. So, for example, let's say our population mean is 30, but a sample of 64 people gives us a mean of 32. If we know the population standard deviation is 8, our standard error is 8 divided by the square root of 64. That's just 1. So we calculate our z-score, 32 minus 30, divided by 1. That gives us a z-score of exactly 2. Now, if our critical value for conviction is 1.645, our score of 2 clearly exceeds it. The evidence is overwhelming. We reject the null hypothesis.
But wait, what if the population standard deviation is totally unknown? I mean, in the real world, this is incredibly common. When this happens, we pivot to the t-test. The formula looks almost identical, but instead of the population standard deviation, we plug in the standard deviation of our specific sample, denoted by a lowercase s. Now, doing this introduces a slightly wider margin for error, which we have to account for using a concept called degrees of freedom. You can think of this as a statistical penalty for having to estimate our data from a smaller sample. So let's say our baseline mean is 75. We test a sample of 25 items and find a mean of 79, with a sample standard deviation of 10. Our standard error becomes 2. Our t-score is 79 minus 75 divided by 2, giving us a t-score of 2. Looking at our t-distribution with 24 degrees of freedom, we find this still exceeds our threshold, so once again, we reject the null hypothesis. And finally, what about situations where we aren't testing averages, but we're looking at percentages or fractions? That is exactly where the proportion test comes in. Imagine a company is out there aggressively claiming a 95% customer satisfaction rate. That's our initial assumption, our p-0 of 0.95. But then we survey 200 of their customers, and only 180 say they're satisfied. That means our sample proportion, p-hat, is only 90%, or 0.90. When we plug these numbers into our proportion test, the calculation yields a z-score of negative 3.24. That is a massive deviation from their claim. The math absolutely proves their 95% claim is highly improbable given our sample. So we definitively reject the null hypothesis.
Okay, section 5. Let's tie the whole shebang together with the 6-step procedure. What we've been doing actually illustrates the exact 6-step procedure every statistician follows from start to finish. Step 1, state your hypotheses to find your null and alternative clearly. Step 2, select your significance level. Pick your alpha, usually 0.05, to set your standard for conviction. Step 3, choose the test statistic. Figure out if you need a z-test, a t-test, or a proportion test based on the data you have. Step 4, compute the statistic. Do the math and find your ZRT score. Step 5, determine the p-value or critical value to measure the real weight of your evidence. And finally, step 6, make your decision and conclusion. You either reject or fail to reject the null hypothesis. You strictly follow these 6 steps, and you are conducting rigorous, mathematically sound statistical analysis. As we close out this explainer, I want to leave you with a really critical thought. It's a trap so many people fall into. If we run our test and our math fails to reject the null hypothesis, did we actually prove that the null is absolutely true? Or, much like a courtroom finding a defendant not guilty rather than completely innocent, did we simply lack the evidence to convict them this time around? Think deeply about that distinction. Because in the world of statistics, an absence of evidence is absolutely not evidence of absence. Keep that in mind the next time you see a bold statistical claim making headlines. Thanks so much for joining me on this explainer, and as always, keep questioning the data.